Good morning, ladies and gentlemen. Let's take a look at our Bellwork for today. We need to be able to find the average value of a function over a specified interval. So if we're given an original function, f of x is given by e to the x over 2, and an interval of 0 to 3, we can calculate the average value simply by using our formula for y average. We know the average value of my function is given by the integral of my function from a to b. Right, that's summing up all of those function values, and then dividing by the length of the subinterval in which they occur. So that's dividing by b minus a. So that's my general formula. For us, we can go ahead and evaluate using this particular function f over the interval 0 to 3. So it looks like 1 over 3 minus 0. My integral is from 0 to 3. My function is e to the x over 2. With respect to x, I'm ready to rock style this to the top. So I've got my 1/3 output, just chilling, constant multiplier. Then I'm going to go ahead and find an antiderivative function for my integrand function, e to the x over 2. And I know that an exponential function is cyclical in its derivatives. And so the derivative of an exponential function is itself. Therefore, I know the antiderivative for e to the x over 2 must include itself as well. So I'm going to have an e to the x over 2. However, if I were to differentiate this function e to the x over 2, it would spit out a times the derivative of the exponent in accordance with the chain rule. So it would spit out a 1/2. And did I have a 1/2 in my original integrand? No, so I need to account for that by providing what constant? A 2, and so I'll go ahead and provide that 2 out front. There's an antiderivative function for my original integrand. And now I'll evaluate that from 0 to 3. Raise your hand if you have the correct antiderivative function, the 2e to the x over 2. Great. So that's a good setup for today. Now I'll continue. It looks like I've got 2/3. And I'll evaluate e to the 3/2 minus e to the 0. I can get an exact answer. Go, Gadget Arm. And now I get e to the 0 is 1. So I get 2/3 e to the 3/2 minus 1. And I saw several of you did an approximation for that and got about 2.321. Did you guys get about 2.321? Correct? So that's about 2.321. Awesome. So raise your hand if you already got that. So who got that? Great. Now let's go ahead and take a look at our picture and make the connection, the graphical connection between the perfect height rectangle we were talking about before. And so from 0 to 3, right, from 0 to 3, we can construct a rectangle whose area is exactly the same as the value of the definite integral. So the definite integral from 0 to 3 would be given by this sandbox region. Even distribution there, Tyler, an even distribution. And now I'm going to go ahead and draw the rectangle with the same area as that. Its perfect height is given by y average. So if I take that average value and multiply it by 3, the width of my subinterval, I should get base times height equals the exact value of the definite integral. So where is that? It's about 2.32, so right about 1, 2, 2 point, yes, exactly right there. Oh, good drawing. Thanks. Let's do it. Very nice. And if we had our calculus shovel, we could start shoveling and lop this sand off, this red sand that's sticking up above the y average, and then push it down and scrunch it down in here, and it would fill up that space exactly, right, where the rectangle is over the function. And so we've created, right, we've created our y average right here, multiplied by the length of my interval. That was b minus a. And what does that equal? Well, it equals visually that red sand box integral from a to b of f of x dx. And we see where our average value formula is hiding. If we divide this over by b minus a, then we're left with our y average. We started the party. And so I was hopeful that you'd get a connection between the mean value theorem for definite integrals, right? I'm sorry, the mean value theorem for integrals, and our notion of the definite integral, our y-average formula as well. Cool. What questions do you guys have about our Bellwork? That's a darn good picture. All right, let's go ahead and take care of our homework check, and I'll pause the recording while we do that. Okay, ladies and gentlemen, thank you for your help. At this time, I want to go ahead and take a snapshot, right, of the past couple of days. So we worked to develop conceptually the fundamental theorem of calculus over the last 2 class periods, as well as average value, right, and the mean value theorem for integrals. So let's see how these all connect. We know that big F is an antiderivative of little f if and only if the derivative of big F equals what? Yeah, equals little f. So our definition for the antiderivative, big F is an antiderivative of little f if and only if the derivative of big F equals little f. Well, this then is directly related to the fundamental theorem of calculus. Calculus antiderivative part, and calculus too. They're like a spawner. Calculus. The derivative with respect to x of an integral expression, right, gets me that integrand. So I can do this the long way and find an antiderivative for this little f, call it big F. Evaluate at the upper, so big F of x. Evaluate the lower, big F at a, and then subtract the two. So I get big F of x minus big F at a. When I differentiate that difference, the derivative of big F is little f of x minus the derivative of big F at a is just a constant, and the derivative of a constant is 0. So if we did this the long way, right, we get the derivative of, well, I'm going to go ahead and write it. We get the derivative of big F of x minus big F at a. We know the derivative of a constant is just 0, so if I differentiate big F of x, I get little f of x. So maybe it's helpful to have that long way there. In the future, we can go right from the left-hand side to this right-hand side. So then our antiderivative part of the fundamental theorem of calculus with the chain rule, right, includes the times the derivative of the base. That is, the derivative of that integral expression will be the integrand function evaluated at the upper limit. But because my upper limit is itself a composite function, a function of x rather, I'm going to multiply times the derivative of the upper limit. And so this is the chain rule for the antiderivative part. We should generate the integrand function evaluated at the upper limit, in this case h of x, and then times the derivative of that upper limit, h of x, so long as my lower limit is a constant. And it can be any constant, as we've seen, because the derivative of that antiderivative function evaluated at the lower limit is just a constant, and the derivative of that is 0. Awesome. So I'm feeling pretty good thus far. We've got our fundamental theorem of calculus antiderivative part. We've got our definition of the antiderivative, but we still need our definition of the definite integral. That's not to be confused with the fundamental theorem of calculus evaluation part. I know the left-hand sides look very similar. Well, they are, but I don't want you to lose sight of the fact that our definition of the definite integral came from the limit of Riemann sums, the area of individual rectangles, and as I let the number of rectangles n go to infinity, right, we filled up that irregularly shaped region exactly, and we're left with the exact area. So the definition of a definite integral is a limit of Riemann sums. We can go ahead and write that as the limit as delta x goes to 0 or as n goes to infinity. I choose to do the n goes to infinity of the sum for my index k equals 1 up until the nth rectangle of the area of those rectangles. And the area of a typical rectangle would be given by the function value at a typical x value. Call it, well, I'll call it c sub k, multiplied by the width of that typical rectangle. I'll call it delta x sub k. The product then would represent the area of a single rectangle, and if I summed up, right, as my sigma notation, if I summed up all the individual areas of those individual rectangles, and there's an infinite number of rectangles, right, that I'd be left with the exact area in between the function and the x-axis on the interval a to b. All right, that's different then my evaluation part provides me the connection, right, between indefinite integrals and definite integrals. I now can evaluate that definite integral by finding an antiderivative. And so this is where everything comes together. I can now find that antiderivative function, call it big F of x, evaluate at the upper, evaluate at the lower, and subtract the two. So big F of b minus big F of a provides me with our exact and algebraic calculation of a definite integral using indefinite integrals. The fundamental theorem of calculus is the bridge between those two things. Oh, gosh, that's so exciting to me. Slightly less exciting to you, perhaps, right? But this is a big deal, so that's pretty cool.
So excited.
I feel like, this is just personally, but I feel like, again, now seeing it in BC, you've had a chance to digest, and you're coming back to it, and hopefully you're seeing how the pieces fit together just a little bit better. All right, so let's go ahead and do a warm-up. Today, you already know the cat's out of the bag. We're going to evaluate indefinite integrals, and you know that's synonymous with antiderivatives. But to be good at antidifferentiation, you have to be good at differentiation. So at this time, I ask that you differentiate this and check with your partner. Do it yourself first, then check with your partner, and then only after you've checked with your partner, raise your hand if you have the same thing. So I tried to make a couple links here just to get the party started. Okay, ladies and gentlemen, let's go ahead and share our result for f prime of x. Given f of x is cosine to the fifth of e to the x cubed. So you said you guys agreed? Sydney and Tyler? Okay, so then go ahead and share your expression f prime of x with the class, please.
Negative 15 x squared cosine to the fourth e x to the third, and then times e x to the third, and then times sine of e to the x to the third.
Whoa. Okay, thank you for sharing. Let's go ahead and take a look. Ready? Where did these individual pieces come from? Well, we need to be able to differentiate a composite function in accordance with the chain rule. So let's go ahead and check Tyler and Sydney's answer. Here we're going to go exponent, right? And overall, this is a cosine to the fifth. So the cosine to the fifth. And so this is a power rule. Overall, this is a power function, where my current base is cosine of the x cubed. And my exponent is 5. So let's do our derivative rules. Our derivative of a power function is exponent times the base to the 1 less times the derivative of the base. Well, the base is itself a composite function. That's the ugliest E I've ever seen in my life. I apologize for having exposed you to it. There. I can't eat. Yeah. It's going to get you. It's going to get you. So I need to differentiate the base. What? Well, the derivative of cosine is opposite of sine. So there's the negative that Tyler shared. Here's the sine with the angle, e to the x squared. And then times the derivative of the angle. Well, the derivative of e to the x squared, that's the derivative of exponential, which is the exponential function itself times the derivative of the base, the derivative of the exponent, 3x squared, and there's my 3 times the 5 is the 15. Put it all together, and this is what you got. Raise your hand if you have the same thing. So if you have the same thing? Yes! Yes! That's great news. All right. Get rid of that nasty E messing up our PDF. So, what's up? Well, today we're going backwards, right? And today we're going to be able to evaluate the indefinite integral of x squared e to the x cubed cosine of fourth e to the x cubed with respect to x. Notice the lack of limits on my integral symbol. That means this is an indefinite integral, right? And an antiderivative. So I'm trying to find an antiderivative function such that when differentiated produces that. And so, gosh. These look very similar except for what? What am I missing here? Yeah. And so how are you going to be able to integrate that? I think I left off the sign. I don't know how we're going to be able to integrate that because we don't have the derivative base. So that's no good. We need sine of e to the x cubed. We can fix that. So we need sine of e to the x cubed. Cubed. Now do we have enough?
Yep.
Well, yeah, except that we didn't have the negative 15. So you've just seen that the derivative of cosine to the fifth e to the x cubed is negative 15 of that, right? And so the idea is that we need to account for the derivative of the inner function in order to be able to go backwards. It's all about the chain rule and providing that derivative of the base, or that derivative of the angle, or that derivative of the exponent, right? And so we've got all of these rolled into there. So now what can we do? Well, we could go backwards, except we need to provide for that constant. And so remember, we can provide a constant multiplier, no problem. If we had a times negative 15 here, if we had times negative 15 here, then we'd know my antiderivative was exactly that, cosine of the fifth e to the x cubed. But we didn't have that, so what do we need to do to account for that? Only provide a negative 115. Can we do it? Okay, and anytime we evaluate an indefinite integral, what must we be sure to include? Let's see, for my constant of integration. Right, we could have had any constant included in my antiderivative function, and when differentiated, right, it would disappear because the derivative of a constant is 0. Well, what that warm-up was meant to do was get us thinking about the relationship between different parts in my integrand function. And so the key here is seeing which piece is the derivative of which, or a portion thereof. And so I tried to structure these so we could pick out the derivative of the base, or the derivative of the angle, or the derivative of the input, right, or the derivative of the argument, whatever it may be in the chain rule for the given rule. So as you scan this problem, I can see there's two distinct parts. I've got an x squared plus 4 to the 7th power rule, and I've got a 2 to the x linear function. Well, I, of course, meant for this 2x dx, right, that 2x dx, to be the derivative of the base in that power function. And so long as that derivative of the base is present, right, I know I've got both parts from my chain rule, the derivative of the outer function with the inner function, and then times that all important squiggle underline part, the derivative of the inner function. So if I have that piece, then I can go directly backwards using my overall rule. This overall is a power rule, so I'll add 1 to the exponent and divide by the new exponent. So what do I get? Well, I get x squared plus 4 all to the 8th, and then divided by 8, and then plus c. We don't think that's right? Well, we can always differentiate our antiderivative and see what we generate. And so it looks like I got 8 times x squared plus 4 to the 7th all over 8 plus the derivative of constant and times the derivative of the base times 2x, and that's exactly what we have because the 8's cancel out. There's my original. Okay, starting small, little steps. What is required to provide for the derivative of the base in that second one? Go ahead and tell your partner and then be ready to share. Almost got it, but not quite. We don't have it. Is that the second time? Okay, so in order to be able to integrate this, right, we need to provide for the derivative of the base. And we almost have it, but not quite, right? What are we missing there? What are we missing? Brendan and Vivian?
3.
Yeah, if we had a 3x squared, then we would have the derivative of the base in that power function x cubed minus 5. The derivative of x cubed minus 5 is 3x squared. And so if we had times 3 here, then we'd be able to go right to my power rule, add 1 to the exponent, divide by the next one. But we didn't have a times 3 here, so to account for that, we can put a 1/3 there. And now we'll keep the expression equivalent to the original because 1/3 times 3 is 1. And now I can go ahead with my power rule. So I'll add 1 to the exponent and divide by the new exponent. What was my base? X cubed minus 5. So I add 1 to the exponent, divide by the new exponent, and I don't neglect to include the plus c. All right, where's my 1/3? Right
There we go.
here. And we can make that prettier. We could go ahead and do 1/21 out front, or we could do all over 21. Either one's fine. So 1/21, well, I'm ever the pessimist, so I'm going to go ahead and check that by differentiating to make sure that we haven't made a mistake. So far I've had 2 derivative of the bases left off today, so that's not good. So I'm going to do a check and make sure we're doing it correctly. Exponent times the base raised to 1 less times the derivative of the base. And times my derivative base is a 3x squared. And now I see that my 7 times 3 is 21, times 1/21 is just 1, and I'm left with my x cubed minus 5 to the 6th, and then the x squared. So math works, that's good news. All right, slowly stepping up. So now I want you to consider the different pieces here. Enough of our little polynomial, right, power rules. Let's take a look at this integrand. What I want you to do is go ahead and tell your partner a plan of attack. Which part is the derivative of which? How can we attack this problem? By providing a derivative of the base, right? It is. All right. So what's the relationship between the pieces? What did you guys come up with? Go ahead and share with the whole class. So what's the relationship between the pieces here? Riley and Grace?
Cosecant squared is its derivative of cotangent.
So cosecant squared is the derivative of cotangent, right, or a portion thereof? Absolutely. So we've got our cosecant squared double underline is acting as the derivative or part of the derivative of that base cotangent in the power function 1/2, right, base to the 1/2. Well, you don't quite have it all, right? So what's the derivative of cotangent? Opposite cosecant. Very nice. So I'm going to go ahead and include a negative sign. Right? If I had a negative sign, I could go right to my power rule, add 1 to the exponent, divide by the new exponent. However, I didn't, and so I need to account for that. Negative times a negative, right? Keep it the same as the original, and I see that my antiderivative function, right, would have a negative. This is going to be cotangent of x to the 1/2 plus 1 is 3/2. Divide by the new exponent is dividing by 3/2. That's the same as multiplying by 2/3, right? I like that. And then plus c, and we can make that a little bit prettier. So this becomes negative 2/3 cotangent of x to the 3/2 plus c. How do we do? Very good? All right. So, right about now is when we begin wondering, okay, so would U substitution have been a better strategy? And so, if you're comfortable providing that constant, in this case it was just a negative, you can continue to do so informally except for 2 different cases. Those 2 different cases involve, right, algebraic substitution, where we can't simplify and recognize a rule that we currently have, or a change of limits problem, where they give us a changed variable and our limits on the integral symbol are different, so we have to complete a U substitution in order to determine the proper answer. All right, so let's go ahead and take a look at the next one. Whew. So I know that we had two missing derivative of the bases. So is this another, right? Is this another missing derivative of the base typo? Nope, this isn't, right? So I try to rewrite in such a manner that I do recognize the rule. Right now, can I use the power rule? Why can't we use the power rule right now? Add 1 to the exponent divide. I mean, clearly it's not a natural log because I'm on the bottom to the second, right? So this would be a power rule. Only on the bottom to the first is even a candidate for natural log rule for antidifferentiation. Why can't I use the power rule? Like I can use the power rule. It is a power function, but I can't use the power rule. How come? Well, you want to use the power rule?
No.
No, Vivian?
There's no like cosine.
Yeah, if I had a cosine of 5x, right, then I would have the derivative of the base or a portion thereof. I need that derivative of the base in accordance with the chain rule in order to go backwards. If I don't have a cosine of 5x, I'm unable to use the power rule because I don't have the exponent times the base raised to 1 less times the derivative of the base part, right, that completes the chain rule. So what are we going to do? Well, we're going to try and use algebra or trigonometric identities to rewrite this in such a form that I do recognize the rule. So how could I try rewriting this? Any ideas? No ideas? Ni idea? We're stuck. It's early in the class period. I'm going to rewrite sine squared on bottom with the quotient, the reciprocal identity. What's 1 over sine? Right? So I'm going to rewrite this as cosecant squared. I was trying to get a little warm up there, huh? So if I rewrite sine squared on the bottom as cosecant squared on top, how does that help me? Well, because now I do have a trig function derivative, right? I have a rule that will allow me to integrate that. The derivative of cotangent is cosecant squared, yes? So I don't want you to think that we have to use substitution every time, or, right? Because we could use algebra or we could use a trigonometric identity to rewrite. We're trying to make the integrand in something recognizable that we do have a derivative rule for. All right, let's go backwards then. What do we need? Well, we need a couple things. I'm not ready to go straight to my answer. I need to provide for the derivative of the angle, right? And there's a negative sign too. So if I had a 5 here and a negative sign, so if I had a 5 for the derivative of the angle, and I had a negative sign, right, then I would know this goes to cotangent of 5x, is that right? But I didn't have either of those things. So what do? I need to provide that in my antiderivative. I need a negative 1/5 cotangent of 5x plus c. And I need a check. So negative 1/5 cotangent differentiates to opposite cosecant squared with the angle times the derivative of the angle. And let's start canceling. I've got 5 times 1/5. I've got negative times a negative. And I have cosecant squared 5x. That's equivalent to 1 over sine squared of 5x. Okay, math works, and we're doing okay. All right, so are you okay with the informal provision of derivative of the base? So far, we don't have to do substitution yet? Okay. So then what gets trickier? Well, I don't know necessarily. Why don't you go ahead and do this one with your partner, and then we'll do a check. So now's where we're not so bad, the top one. Okay, ladies and gentlemen, let's go ahead and take a look. So we've seen in the early examples that so long as we can provide for the derivative of the base, right, the derivative of the angle, the derivative of the inner function, then we're ready to go with our go-to rules, right? And so I'm recognizing this here as two different pieces. And I saw in your discussions, and as I walked around the room, that cosine of theta is there acting as part of the derivative of this base, the 3 minus sine theta, in an overall power function, whose current exponent is -2. I'm going to go ahead and kick that 7 out front, though, so that I don't trip over it, and then show the actual derivative of the base, so that I'm ready to go and don't make any mistakes. So I'm going to go ahead and write the 7 out front. Then I'm going to put my integral of, and I'm going to leave my cosine of theta on top. And then I'm hoping that that's going to act as the derivative of this 3 minus sine theta, which is currently, right, overall to the negative 2 power. So what's the derivative of the base? Well, negative sine theta differentiates to negative cosine of theta. So I would need a negative cosine theta in order to apply my power rule here. So what do? Well, I provided a negative, so I must provide a negative in my antiderivative. The 7 sticks around for the party. I'm ready to go with the power rule. I know my current exponent is negative 2, so I'm going to add 1 to the exponent. That's 3 minus sine theta to the negative 1, and divide by the new exponent. When I divide by negative 1, I go ahead and cancel out negative over negative is positive. So don't I get positive 7 over? Don't I get positive 7 over 3 minus sine of theta plus c? Where's your enemy got that? Did we get the positive 7? Positive 7? Wait, no, so close, right? So, yeah. Riley, you got it? Awesome. Way to go, you guys. So, remember, we can check every single time. By differentiating, we can check our antiderivative, and I think that that's an important skill. You can see we're going to go gadgeting around this already. Because I want to check. Right? I want to check every time. So I get 7 times current power is negative 1, so negative 1 times 3 minus sine theta to the negative 2, then times the derivative of the base. And the derivative of the base is 3 minus sine theta differentiates to negative sine theta differentiates to negative cosine theta. And let's grab our favorite marker. Negative times negative, positive 7 cosine theta over 3 minus sine theta squared. We win, math works. Yes! So sweet. Okay, so are we thinking we need, let's do a little bit more space here. So what I'm going to do is I'm going to clone page. And clear ink. All right, so as you guys tackle this bad boy, right, we've got a couple of different ideas here. So we've dealt with a variety of power functions thus far. Is this going to be a power function? Or is this going to be a power function? How come? Why can't this be a power function?
Raised to the negative 1.
Yeah, right now with this quantity on the bottom to the first power, this would be a candidate for natural log. I can't use the power rule because if I add 1 to the current exponent, negative 1, right, I get 0, which is fine, but dividing by the new exponent would be dividing by 0. And that's a no-no too, Daphne. Well, so then now about natural log. If I have quantity on the bottom to the first power, if I'm thinking about x squared plus 36 all to the first power, right, then I could use natural log. Alas, I can't use natural log. Why can't I use natural log? You're going natural log?
Yes.
Good. Good recognition that there was a quantity on the bottom of the first. That's a candidate for natural log. Why can't I use natural log?
No x.
Yeah, we don't have an x. We don't have a derivative of the function. So what's the natural log rules for differentiation? The derivative of natural log of a function is 1 over the function times the derivative of the function. That would spit out a 2x, right? And I don't care about the 15. We can move constants, multipliers, whatever we want. But I don't have an x. So what am I going to do? Trig identity. Yes! We're going to do trig identity. No! Yes! It's a trig rule, kind of. Right? So what does it have to be? Well, anytime I have that squared and then plus, I'm thinking inverse tangent. But my inverse tangent rule has 1 plus input squared. And right now I have 36 plus input squared. And so I can't do inverse tangent right now. Right? So what am I going to do? Algebra. So I've got my tool bag. We already used trig identities for my tool bag. So now we're going to go ahead and use some algebra to rewrite this and make it look like inverse tangent. So how are we going to do that? Well, first things first. Let's get that 15 right out of there so I don't trip on it. Now let's go ahead and do some factoring. So I know that if I took out a 36 from the bottom, then I'd be left with 136 x squared plus 1. Hey, wait a minute. Then I would have, right? Then I would have 1 plus argument squared, right, times the derivative of the argument. And so I've got the 36 on bottom. I'm going to move that out of here as well. So I'm still going. I've got 1536 out front. Integral of, and now one more reframe. I want to make this look like 1 over 1 plus the input squared. If I can rewrite that angle as input squared, right, I'll be all set up for my inverse tangent rule, which Sydney already pointed out this was going to be true. So how could I rewrite 136x squared as something quantity squared, right? Kobe?
X over 36.
Almost, right? If I want to write this as input squared, x over 6, right? X over 6 is my input. Yes? And why do I write it like this instead of leaving it as 136x squared? Because I need to provide for the derivative of the input in accordance with the chain rule. And by writing it like this, I can see that the derivative of my input isn't, right, 136. It's what? Well, it's 1/6. So if I had 1/6, here's my derivative of the input. Here's 1 plus the input squared, and I'm ready to go. But I had to provide the 1/6. So what do I need? I need a times 6 over 1 out front. Now I think we finally got it. So I've got 1536 times 6 is 15/6, which is going to reduce nicely for us in just a minute, times, there's my derivative of the input, so I'm ready to go with inverse tangent of x over 6 plus c. This in turn equals, divide out of 3, so I get 5 halves, is that right? 5 halves? Inverse tangent of x over 6 plus c, and there's no way I'm boxing that until I check it. So I'm going to go ahead and check that because I've got the 5 halves. Let's check it and see what we get. So the derivative of 5 halves times inverse tangent differentiates to 1 over 1 plus input squared times the derivative of the input, right? That in turn equals 5. Uh-oh, that's not good. 5/16. So that's 5/12. Yes, 5/12 times 1 plus x squared over 36. Yes? And we want to make it look like that. So what would I have to do here? Can we get all the way there? Common denominator. 36 plus x squared over 36. On the bottom. Times 5/12. And dividing by a fraction is the same as multiplying by the reciprocal. So this 36 goes up on top. Ah. And what's 36 divided by 12? Times the 5 on top is over.
Killing it.
Killing it all day, every day, 24/7, 365. Right here. I'm glad I cloned that page. All right. So I've tried to mix in some different examples where we dealt with power rule, right? Why can or we can't use the power rule? Natural law, we need the derivative of the input, we need the derivative of the base, we need the derivative of the function to provide for the chain rule. What I want you to do, however, is not lose sight of the fact that algebra and trigonometric identities could be an easy way to break through a potential roadblock. And so as you consider this one, we see that, yes, in a power rule, 2x squared minus 3, if we interpret that as the base of a power all to the first, the derivative of 2x squared is 4x. And I've got an x, except that's not really an x. It's x to the negative 1. Is that the derivative of 2x squared minus 3? No. Is this a power rule? Antiderivative? No. Not as written. And so what can we do?
Algebra.
Algebra, comma, baby. I know that a summer difference in the numerator of a fraction can be rewritten as, right, summer difference of individual fractions, each with the same denominator. So what do we do if we have summer difference on top? Break it up, break it up. We can rewrite this bad boy as 2x squared over x minus 3 over x. That's equivalent to the original. Why is that helpful? Well, that's helpful because 2x squared over x reduces to 2x minus 3 over x. And now I can go term by term and find the derivative. Go ahead and finish that one out. Don't forget your bars. I made super elongated bars, just so you don't forget. Yes? No?
Absolute value, but yeah.
Yes?
Yep.
So if I'm using natural log as an antiderivative, I must purposely provide absolute value bars. How come? Well, this reciprocal function, 3 over x, is a hyperbola in quadrants 1 and 3. It exists for both positive and negative inputs. My natural log function, however, only exists for positive inputs, so to rectify that, I have to include absolute value bars, and now I've got positive and negative inputs allowed. Both of them are undefined at x equals 0, so there's no problem there. Cool? That's pretty bomb. All right, so then, gosh, this is another typo, Mr. Fritz. So, it's not. I got this out of the way early. I did the lesson backwards yesterday. All right, so, gosh, that sure looks similar to the top, doesn't it?
Yep. Flip it around.
Flipped around. So what overall rule is this now? Otherwise, it's going to have to be. Power rule? Yes, power rule? Natural log. It's got to be natural log. Can't be power rule. Right? I do have the derivative of the base, right? But the current exponent is
Negative.
yeah, -1 or 1 over, right, the function times derivative of the function. So I must provide the derivative of the function. No problem. If I'm interpreting this as quantity on the bottom of the first, that's a candidate for natural log, but I must provide the derivative of the function. So the derivative of 2x squared minus 3 is 4x. And by golly, if I had that 4x dx, then I can go right to natural log. But I didn't, so I must include a 1/4. Otherwise, we're set. So I get 1/4. Natural log of, absolute value of 2x squared minus 3, close bars, plus c, and a quick check. 1/4 times 1 over the function times the derivative of the function. 4, 1/4, and I get x over, hey, that's the same thing. Math works. Yay. All right. So thus far we've been able to escape, right, the dreaded U substitution. However, there is going to come a time when algebra, right, will fall short for our rewrites. Trigonometric identities won't help, or we've got to do a change the limits problem where all of the limits and the variable, the independent variable has been changed in my multiple choice response. So there are certain times when I have to be able to use U substitution. Is this next problem such a time? No, still don't I still have a summer difference in top? So I can still do breakup. I can still do algebra for this and simplify using my exponent rules. And so I'll still break up and try. If I can't, or if it doesn't help, then I'll just consider U substitution. So let's see. This becomes the integral of x over root x minus 1 over root x with respect to x, which in turn becomes 2 power rules. This is the integral of x to the first over x to the 1/2 over all of x to the 1/2 minus 1 over square root of x is x to the negative 1/2. So I can simply go term by term and apply my power rule. The antiderivative of x to the 1/2, right, is going to be 2/3 x to the 3/2. The antiderivative of x to the negative 1/2, right, I'll keep my sign, becomes x to the 1/2, and then times 2. Because dividing by 1/2 is the same as multiplying by 2. And as always, we say plus c. Okay. Big build, and can we split up the fraction in this one? No. How come? Our quantity, right, is inside the radical as opposed to my radical being a single term there. So I can't break up the fraction here. That sum or difference is inside my square root. So what do? Well, I could use the power rule. No, because x is too much. That's not the derivative of the base. And natural, no. So I'm at a roadblock. Well, by a smart choice of u, I could make it so I don't have a sum or difference inside of my radical, right? And see if that helps at all. And so, well, I don't know if this is going to help or not, though. This could be a roadblock, too. This could be a fast typer. What if I did... This might not work. This is what happens when I make up problems. So, if we choose u to be x minus 1,
Yeah.
right? If I choose u to be x minus 1, I'm working towards a root u, which I think I meant to be on the bottom. And better pause this path more.
Please do.
Okay,
Seriously.
so we have our top and bottom flipped. Is everybody flipped their top and bottom?
No.
Now, by a smart selection of u, I could rewrite this as an algebraic substitution in such a manner that my sum or difference is no longer caught up inside of the radical. And so if I choose u to be x minus 1, I'm going to force it to be radical single term, and then my sum or difference then will be on top, and then I can break up and use algebra. And that was my original intent, so I apologize for that error. Let's go ahead and perform the substitution then. By replacing x minus 1 quantity with u, and x with u plus 1, I'm able to rewrite this in such a manner that I do have antiderivative rules. So I get integral of, go gadget arm, x is u plus 1, over square root of x minus 1 is now square root of u. Dx is equivalent to du, and remember you have to have the same type of independent variable, right, as your integrand function in order to have the same variable in your antiderivative. And now I can break up the sum or difference, which is what I was after. And so then the rest becomes the same. I mean, we had a plus here, but not bad. All right, so I'm going to do one more rewrite and then get to our answer. So this becomes the integral of u over root u is u to the 1/2 plus u to the negative 1/2 and I think we're there. So that becomes u to the 2/3, u to the 3/2. This becomes 2 root u, yes? And then plus c. We good? Awesome. So what's the final thing that we need to include? The final portion includes the limits. So let's go ahead and take a look at our limits. Please note, we could, right? We could find the antiderivative and then evaluate on my upper and lower, and I'm going to do that if we're able to. So do we have to perform a u substitution here? Can I provide for the derivative of the base?
Yep.
We can provide for the derivative of the base. We just need a what? Negative 2?
Yep.
So we'll do negative 2 and cancel with the negative 1/2. So we get negative 1/2. Power rule. and 1 minus m squared. So we've got our add 1 to the exponent. We've got our divide by the new exponent. And because we're doing a definite interval, we don't have to include the plus c. So now we can just go like that. And does this look better? Negative 1/3. All right, so let's evaluate. How do we do it here? So let's see. This becomes negative 1/3. I'll pull that out front, and then I'll plug in 1 for m squared. 1 minus 1 is 0 to the 3/2 is 0. Minus 0 in for m gives us 1 to the 3/2 is 1. So it looks like overall I'm getting 1/3. You guys getting 1/3? Awesome. You can certainly check that using Math 9. All right. I'm just wondering if I wanted to do it for you or not. All right. So, you guys want to use substitution, or do you want to just provide for the derivative base?
Derivative base.
Hey, I'm so glad you guys. Last year was difficult sometimes when everyone used substitution. This is great. So, what's my base? My base is cosine of 2t, right? And then that's all power roll to the negative 3 current exponent. I need to provide for the derivative of base, cosine of 2t, which is opposite of sine, right? 2t times 2, yes? So if I had negative 2, yes? Is that it? So this is my derivative of the base. But I didn't have a negative 2, so I need a negative 1/2. Can we go right to it? So I've got negative 1/2. And I now have to, right, add 1 to the exponent and divide by the new exponent. So this becomes cosine of 2t to the negative 2 divided by negative 2 and then evaluated from 0 to 5 or 6. Goodness. So I've got negative times negative is positive 1/4. And I've got cosine squared 2t on the bottom. I don't think I have to do this parentheses. What do we do? Negative, negative, positive? Yes? Are we good?
Yep.
Okay, so how's this going to work out? Well, I hope nicely. We get 1/4 pi over 6 into t. 2 times pi over 6 is pi over 3. The cosine of pi over 3 is 1/2. Squared is 1/4. Minus 0 in for t times 2 is 0. The cosine at 0 is 1. 1 squared is 1. So I'm getting 1/4 times 1/4 minus 1 is negative 3/4. Is that what you guys are getting? So that's negative 3/16. And we can check out Math 9. Okay. So let's go ahead and make a connection between the two different pieces for our closure. So one thing that I wanted you to get out of today's discussion was, what is the chain rule? What's the derivative of the base? What's the relationship between the two pieces? However, not to lose sight of, right, the fact that sometimes we have to use algebra or a trigonometric identity for a rewrite. And so I made two similar problems here. In each integrand, which part is the derivative of which? What should we choose u to be if performing a u substitution? And then evaluate. We've got an indefinite interval and we've got a definite interval. I'll go ahead and pause and give you guys a chance to work those out. Okay, ladies and gentlemen, how did you interpret number one, the relationship between the two pieces? Brendan?
Secant squared is the derivative of tangent.
Nice. And so if we were performing u substitution, we could choose u to be tangent of x. Then when we differentiated u with respect to x, we get the secant squared x, right? dx part. So that is our derivative of the base. So we're ready to rock and roll with the antiderivative. Overall tangent of x to the first. So this is a power rule. So we get 1/2 tangent squared of x plus c. Did anybody interpret the integrand differently? Everybody did that way? Okay. I saw secant squared as secant x times secant x and grouped as secant x with tangent x. Then the derivative of secant is secant tangent, and we could have integrated the secant function to the first and get secant squared over 2. Wait a minute. If I get secant squared over 2, how in the world can that be the same as tangent squared over 2? Well, 1 plus tangent squared is secant squared, and here's my 1 plus. So that constant, right, that constant could be the 1 plus tangent squared, and there it is. That's pretty interesting. Cool. All right, so do you see the same relationship for number 2? Did you do u substitution? Okay, so if we did do u substitution, we'd choose u again to be tangent of x. Same. On the last part of your assignment, right, it's going to change the limits on you as well and ask you to check and see what that would be. Therefore, the x, right, if I chose u to be tangent of x, then x would be given by inverse tangent of u if you had to do a multiple choice and match the limits. Now, your limits would be inverse tangent of, right, inverse tangent, you should have to be negative 1 to 1, so just wanted you to be on the lookout for that. But we can go right to the 1/3 tangent cubed of x evaluated from negative pi over 4 to pi over 4. And in doing so, we get the tangent of pi over 4 is 1, cubed is 1, minus the tangent of negative pi over 4 is negative 1, cubed is negative 1. So I get 2/3. And that's what I got yesterday. Raise your hand if you had 2/3. You get 2/3 for the second one? Yes! You guys, I didn't have the printable. I ran out of paper for the one side, and so we can group chat that bad boy. But I'm going to stop and save the recording.